Have you heard of the hyperbolic functions? I'm sure some of you have. These functions have properties very similar to trigonometric functions. Consider these two graphs. The graph on the left is a branch of a hyperbola whose equation is x squared minus y squared equals 1, while the graph on the right is a unit circle whose equation is x squared plus y squared equals 1. Both of them are centered at the origin. Look at the points on both graphs. Just as the values of cosine of t and sine of t, for some values of t relate to the coordinates of the points on the unit circle, the values of hyperbolic cosine of t and hyperbolic sine of t for some values of t relate to the coordinates of the points on the right branch of the given hyperbola. Hence, what we'll be dealing now are what we call the hyperbolic functions. Hyperbolic functions may be written in terms of e, or in terms of exponential expressions. The hyperbolic sine function, okay, so hyperbolic sine of x is equal to e to the x minus e to the negative x over 2. The hyperbolic cosine function, or hyperbolic cosine of x, may be written as e to the x plus e to the negative x over 2. This is read as hyperbolic tangent. This is read as hyperbolic cosecant. This is read as hyperbolic secant. And the last one is read as hyperbolic cotangent. And they have their respective definition in terms of e. This means that you may always write these hyperbolic functions in terms of e. Hyperbolic functions also have identities, very similar to the identities of trigonometric functions. If you'll notice, these hyperbolic identities are almost the same as the trigonometric identities, but sometimes they differ in signs or in the operations. These identities may also be used to simplify hyperbolic functions or hyperbolic derivatives. Take note that these are the reciprocal and quotient identities. These are the identities derived from the Pythagorean theorem. These are the double angle identities, and for some indifference of two angles. The differentiation formulas for hyperbolic functions is also almost the same as differentiation formulas for the trigonometric functions, but be careful with the signs. The derivative of hyperbolic sine of u is equal to hyperbolic cosine of u times du. The derivative of hyperbolic cosine of u is positive hyperbolic sine of u du. The derivative of hyperbolic tangent of u is hyperbolic secant squared of u du. Now take note that the derivative of hyperbolic secant of u is negative hyperbolic secant of u, hyperbolic tangent of u du, and so on. Be careful with the negative signs. Differentiating hyperbolic functions is like differentiating trigonometric functions also. When simplifying, we also apply identities. Now let's have some examples. Let us find the first derivative of the following functions. The first function is y equals hyperbolic cosine of x to the fourth. So in here, we will be applying d24. So we have to write our function in the form hyperbolic cosine of u. Okay, so in the given function, u is equal to x to the fourth. So using d24, y prime, or dy over dx, is equal to hyperbolic sine of u, where u is x to the fourth, times du, where u is x to the fourth. So we'll just get the derivative of x to the fourth, and that will give us 4x cubed. So I'll write 4x cubed first, and then copy hyperbolic sine of x to the fourth. Okay, this is already simplified, so this is the derivative of the function. The function is in number 2 is y equals hyperbolic cosine of x to the fourth times hyperbolic sine of x to the fourth. Take note that in this function, hyperbolic cosine of x, the whole function is raised to the fourth, and hyperbolic sine of x is raised to the fourth also. Unlike in number 1, only x is raised to the fourth power. Okay, so since this is a product of two hyperbolic functions, we use the product rule to differentiate, where the first factor is u in the product rule, and then the second factor is v. Okay, so using the product rule, the derivative of y with respect to x, denoted by y prime, using power rule, is hyperbolic of cosine to the fourth x times the derivative of v, where v is hyperbolic sine to the fourth x, plus hyperbolic sine to the fourth x times the derivative of u. Excuse me, so the derivative of hyperbolic cosine to the fourth x. So let us take the derivative of u and the derivative of v. So that's the derivative of hyperbolic sine to the fourth of x using power rule. In the power rule, the base here is hyperbolic sine of x. So using the power rule, this is 4 hyperbolic sine of x cubed times the derivative of the base, hyperbolic sine of x. Okay, so what we'll have is 4 hyperbolic sine of x cubed times the derivative of hyperbolic sine is hyperbolic cosine of x. Alright, so we can just simplify our answer later on. Get the derivative of hyperbolic cosine to the fourth x. Using power rule also, we'll have 4 times the hyperbolic cosine of x cubed, okay, times the derivative of the base. The base here is hyperbolic cosine of x. So we'll have 4 times the hyperbolic cosine of x cubed times the derivative of hyperbolic cosine of x is hyperbolic sine of x. Alright, so we go to y prime, we go back to y prime, and y prime is equal to hyperbolic cosine to the fourth x times the derivative of hyperbolic sine to the fourth x, which is equal to 4 hyperbolic sine of x cubed times hyperbolic cosine of x plus hyperbolic sine to the fourth x times the derivative of hyperbolic cosine to the fourth, which is equal to 4 hyperbolic cosine of x cubed hyperbolic sine of x. We may factor out the common expressions between the two terms, and the common expressions are 4. We have the power of hyperbolic sine of x. Okay. Looking at the exponents of hyperbolic sine of x, in the first term, the exponent is 3. In the second term, the exponent is 5. So the smaller one is 3. So we factor out hyperbolic sine cube of x. And then also, hyperbolic cosine of x is common. If you try to look at the exponent of hyperbolic cosine of x in the first term, it's 5. In the second term, it's 3. So the smaller of the two is 3. So factoring this expression from the two terms in y prime, we'll have in the first term, we'll be left with hyperbolic cosine of x raised to 2, or squared, because we factored out 4 hyperbolic sine of x cubed and hyperbolic cosine of x cubed. In the second term, we'll be left with hyperbolic sine of x squared also. Now, if you'll try to look at this, and then this identity, okay, you'll see that the encircled portion in y prime is equal to hyperbolic cosine of 2x. Okay, so we can write our answer as 4 hyperbolic sine of x cubed times hyperbolic cosine of x cubed, and the encircled portion is equal to hyperbolic cosine of 2x. We can take this out as our final answer, y prime. So this is the derivative of the function. In presenting our final answers involving hyperbolic and trigonometric functions, we always try to avoid having fractions in our final answers or having several terms also. So in this case, we only have one term, so I think this is enough. In functions involving both exponential and hyperbolic functions, Take note that you may always simplify your answers or the function itself using the definition of hyperbolic functions in terms of E. Okay, so in this case, we may write the hyperbolic cosine of x using the definition that I gave you a while ago. Okay, you may write it as hyperbolic cosine of x is equal to e to the x minus e to the negative x over 2. I'm sorry, this should be plus for hyperbolic cosine of x. Okay, over the same denominator, e to the x. Alright, so when we simplify this, we'll have e to the x plus e to the negative x over 2 times 1 over e to the x. Alright, so that's just y equals e to the x plus e to the negative x over 2 e to the x. So writing the two terms in the numerator separately, we'll have e to the x over 2 e to the x plus e to the negative x over 2 e to the x. And then simplifying the function further, we'll have the first term be equal to e to the x over e to the x is 1. So that's just 1/2. Okay, and then the second term is actually 1/2 e to the negative 2x. Okay, when this e to the x in the denominator is written in the numerator, its exponent will become negative x. So e to the negative x times e to the negative x is just e to the negative 2x. Okay, so when we differentiate, it will be easier for us to do that. Instead of having the function in its original form, because in its original form we'll be needing to use the quotient rule. So here, no need. So the first term is just a constant. The second term involves the form e to the u, where u in the second term is equal to 2x. Alright, so we can now get y prime. The derivative of 1/2 is 0. For the second term, we have a constant. Just copy that constant. And then the derivative of e to the u is e to the u itself times du. The derivative of negative 2x with respect to x, that is. So it's equal to 1/2 e to the negative 2x times negative 2. So simplifying by dividing 2, negative 2 by 2 will have negative 1 as a quotient. So this becomes negative 1. So y prime is just equal to negative of e to the negative 2x. So if you want to write your answer with a positive exponent, then y prime will just be equal to negative of 1 over e to the 2x. This is the derivative of the function. So again, whenever the function involves both exponential and hyperbolic functions, you may always simplify using the definition of hyperbolic functions in terms of E. You may choose to simplify the function first using the definition, or you may choose to differentiate first and then simplify afterwards. Here's the next example. Y equals hyperbolic tangent of square root of x times hyperbolic cosecant of square root of x. So we may simplify this function by using some identities, the quotient and the reciprocal identities. So we have to write the hyperbolic tangent and hyperbolic cosecant functions in terms of hyperbolic sine and hyperbolic cosine. So this hyperbolic tangent can be written as hyperbolic sine of square root of x over hyperbolic cosine of square root of x. And then hyperbolic cosecant is the reciprocal of hyperbolic sine, so we may write this as 1 over hyperbolic sine of square root of x. So in this case, we can just divide hyperbolic sine of square root of x by itself, and we'll get 1 over this 1 over hyperbolic cosine of square root of x. And then we know that hyperbolic cosine function is the reciprocal of hyperbolic secant, so this may be written as hyperbolic secant of square root of x. Now we can avoid using the product rule to differentiate this. So we can differentiate this by formula D26. to get y prime. So in this case, u is equal to square root of x. Okay? So we have y prime using d26 is equal to negative hyperbolic secant of u times hyperbolic tangent of u times du, the derivative of square root of x. Now I hope by now you know the derivative of square root of x, and it's equal to 1 over 2 square root of x. So 1 over 2 square root of x, this is negative, hyperbolic secant of square root of x, hyperbolic tangent of square root of x. Alright, so we may just rewrite it. It's negative of hyperbolic secant of square root of x, hyperbolic tangent of square root of x over 2 square root of x. Okay, this is the derivative of the function. The next function is a natural logarithmic function where u is equal to hyperbolic cosecant of x plus hyperbolic cotangent of x. So we'll use the formula for the derivative of ln of u. Alright, so y prime, using that formula, is 1 over u du. So u here is hyperbolic cosecant of x plus hyperbolic cotangent of x times the derivative of the sum of hyperbolic cosecant of x and hyperbolic cotangent of x. Now using the formula number 28 and 27 to differentiate this, we'll have 1 over hyperbolic cosecant of x plus hyperbolic cotangent of x times the derivative of hyperbolic cosecant is negative hyperbolic cosecant of x, hyperbolic cotangent of x, and then the derivative of hyperbolic cotangent of x by 27 is negative of hyperbolic cosecant squared of x. Now in the numerator, we may factor out negative hyperbolic cosecant of x because it's a common expression between the two terms. So factoring negative hyperbolic cosecant of x from both terms in the numerator, from the first term here, we'll be left with hyperbolic cotangent of x. From the second term here, so we'll have plus hyperbolic cosecant of x. So over the same denominator, hyperbolic cosecant of x plus hyperbolic cotangent of x. So these two are the same. So we can just cancel them out because their quotient is equal to 1. Alright. So we'll be left with y prime equals negative hyperbolic cosecant of x. This is the derivative of the function.